True enough, I guess. True enough. Yeah, that's the hard part. I mean, doing the presentation and compiling all that information for an ARP is probably the easier part when it comes to now to writing everything. As I've always mentioned before, writing is not a simple task. It takes years of writing experience to get fairly good at it. But this is what you're going to be doing in the industry. Okay, might as well get started here. Okay, we're getting to the nitty gritty here. Essentially, there's a couple of things I just want to cover as far as the lecture portion. Um, we'll go over a little bit more about the lab. I sent an email yesterday saying that I've taken essentially lab 9 and 10 and made it as 9 for the simple reason that when you're working on 9, when you're calculating your volumetric properties, while you're calculating them, that's probably the time to start plotting your results. The results, thank you, Gord. Stop this for a minute. Set it to a different file here. Just give me a minute here, guys. Okay, thanks for the reminder. And I apologize for that last recording. I don't know, my things go wrong here sometimes, and before I know it, I apologize for that error in the last minute recording. And I'm just glad I was able to get the Google Drive one. So if anybody always has any issues about the recording or haven't seen it quickly, I try and get it uploaded that same day, but that one actually went by me and slipped my mind. I apologize, guys. Okay, we want to cover a couple of things. We're going to look at the fundamentals of asphalt, how it works, some of the key issues about it, some of the things to look forward to with it. And then when we get into the lab, like I stated, I group lab 9 and 10 together. And it might be easier that way. I'll still give you the 2 weeks. You can take it, but we'll discuss the lab portion a little more when we get into it. I'm going to pull up the block schedule here just to kind of go over it a few things, and we'll take it from there. Okay. But you can see this okay. Question. Will it be worth of 2 labs? That's a good question. I'm not sure yet. Typically, if you look at lab 9, the volumetric calculations, if that's typically calculations, what I've done in the past, I mean the recording button on my screen. Sorry, Fabian, I'm not sure what you're referring to. I'll get back to you, Pavel, there for a minute. Something about the recording.
It shows it's recording.
Oh, it shows that it's recording. Yes, thank you. Yeah, thank you very much. Yeah, by all means, guys, sometimes just interrupt and voice yourself, open your mic, unless you can really type fast, which I can't, so I typically talk. Okay, thanks, Fabian. What I've done in the past, typically when there's just calculations involved, That normally I do 5. That lab would be worth 5 marks. When there's more analysis and then there's more writing, like a report, then I would go 10. But because I'm grouping it together, they're all worth the same amount. Depends on how you score. I mean, if you score on the 10 out of 10 on the just the calculations, that's pretty straightforward. So maybe you shouldn't be worth 10. But that's a good point. Leave it with me. I'll give it some thought whether I'm going to make maybe I'll make another 15. That way we'll have, let's say, 5 for the physical calculations of the properties, and then we'll do 10 for the analysis, the plotting of the graphs, and writing out your report telling me what your job mix formula is. This is the whole concept here, is we're trying to determine the mix design. And we're going to do it from the graphs. And we'll get into that when we do the lab after this one. But that's a good question there, Pablo. Thank you.
Hey, John,
Yes, sir.
are we writing 2 reports then, or is it just one for the both?
No, it would be just a one report, because what you would do is you would have all your physical properties calculated. You'd have your graphs plotted, and then your letter report, the job mix formula, would be a summary of saying, based on the physical properties calculated, based on the graphs, the job mix formula is this. So what it actually entails is you got to pick the optimum asphalt content, and typically you select the one at the median of the air voids. Our air voids, we're shooting between 3 and 5, okay? If you look at the City of Winnipeg specifications, it's between 3 and 5. And a lot of agencies, including the Asphalt Institute, say that you select the AC content that gives you 4% air voids. You're in the middle, okay? So why not have a cushion up and a cushion down? You wouldn't want to select anything at 3% because during production, you could be out. So we look at air voids at 4%. And then, okay, and just for an example, let's say it's 5.2% AC. In other words, 5.2% AC will give you 4% air voids. Okay, that's a starting point. Now we go and we look at our VMA at 5.2%. Does it meet 6 to 16? That's what the city requires. Okay, we look at stability at 5.2%. Does it meet? Does the flow meet at 5.2? Density, voids filled with asphalt are going to be just a function of the mix. So there's really no spec for that. But there is flow, there is stability, there is air voids, and there is AC. So that's a starting point. So at 4%, if you check all the other physical properties that the mix has to meet, and it meets spec, there it is. Your job mix formula is 5.2%. And at 5.2%, this is air voids is 4%, stability is this, VMA is this, flow is this, stability is this, whatever. Now, let's say at 4%, let's say one of them is borderline, but let's say at 3.9% air voids, that gives you, say, 5.18, 15 AC. Then you go and you look at that one now and say, okay, at 5.18 or say 5.15, I'm going to look now at 5.15 and see if all those other physical properties meet it. And if they do, then you can go with air voids of 3.9 because you're not too close to 3 and you're obviously not on the 5 end. It's like air content for concrete. You want 5 to 8. When we're designing a mix for air content, you don't want to design for 5.2 because chances are you're going to be at a spec sometime during production. You know, temperature, aggregates change, whatever. So that's why you select the median between 3 and 5. And we'll go over that more when I put up. But that's essentially what all these exercises have been about. From doing an initial sieve analysis on the individuals, blending the aggregates, and then physically separating it on the fractions. And then you would physically mix it. Then you would go and you would heat the aggregate up. You would add your AC to it. You would compact it. You would do your specific gravities. You would do your maximum theoretical densities. Just to be able to plot these. Once we have those values, we can then calculate VMA. Those of you that have done those assignments where you're calculating the air voids and so forth, and the other physical properties on the assignments, you can see how specific gravity always comes into play, air voids comes into play, and so forth. And that's something we can do for a minute here. I want to just show you the block schedule, and that brings me up to my next question. Assignments 8.3 and 8.4. Has anybody had extreme difficulty with it, with those calculations? I put up the solution sheet, but if there's, I haven't heard from anybody. If there's any difficulty, please let me know, because your final exam, you're going to have some problems to calculate, similar to the same format of assignment A3 and A4. Okay, that's those volumetrics, as I call them. Has
John,
anybody had any problems with the assignment? The calculations?
I actually had some questions about the lab we just did.
Okay, and can we leave that till we do the lab, maybe?
Yeah, sure, that's fine.
Yeah, it's just that I, unless it's a real quick question.
Yeah, it was just, are we required to calculate the averages for everything, like your batch sizes and all that, or is it just the average of the GMM and the bulk density and stuff like that?
Oh, no, just the test forms. The test form just tells you to calculate the bulk specific gravity, the maximum theoretical specific gravity, the stability, and the flow.
And that's why they're crossed out to use, they're not required?
The averages?
The averages, like there's an average column, and do you just do the average for the actual GMM? Or
Yes,
the,
yes.
okay,
yes.
just not for everything, just
Oh,
those
no,
things.
no. I mean, you could. I mean, you should get the same answer, really. If you go one way or the other way, it should give you, you should be close, right? But
Yeah, it is, yeah.
typically, you don't do that in the industry. You would run the three briquettes, you would calculate the specific gravity of those three briquettes, and then you would take the average. That's just,
Okay.
I mean, yeah. Put it
And
this way, had you done it and crossed it out, I mean, I'm not going to penalize you on it, but typically forms are set up based on an ISO certification. Each company has certain protocols when it comes to testing. Once you start revising their standards, in-house standards, you're deviating from their certification. But that's neither here nor there for now. Okay? But no, good. Okay, Kevin.
And for the flows, the net flow is just the difference between the start and the peak or the max, and the flow is just times 4 of that,
Times what?
times 4.
You tell me. What'd you get?
Well, that's what we were trying to figure out.
Well, okay. Well, let's stop and talk about it. If you're going to record it in units of 0.25, which is a quarter, right?
Yeah.
How many quarters in 1 millimeter?
4.
Okay.
Oh, so it's divided by 4?
What do you think? If you've got 2 millimeters, okay, your net is 2 millimeters, you can divide it by 4, what are you going to have?
0.5?
Are you between 6 and 16?
No.
So would you divide or?
We'll multiply. That we did multiply. I'm just verifying if that's correct.
You can also divide by 0.25, gives you the same thing, right?
Yeah.
There, see, you just answered your own question.
Okay, thanks.
Always stop and analyze it the other way. I mean, specifications there are for a reason, and I'm not going to give you results that aren't realistic. I mean, it can happen because flows are very, and we'll get into that a little later. Flows are very temperamental. They're, when you look at the plots of a typical flow graph, it's all over the map. And even Astro Institute comments on that. It's just one of those things. Okay. If you read the ASTM procedure for stability and flow, it even mentions that typically the old in the US, it's 0.01 inches. Here it's 0.25 millimeters that we record to, because you'd have such a small number. So it's easier for them to just say flow between 6 and 16 or 8 and 18, whatever the mix dictates.
Okay, thanks.
You're welcome. I put up this block schedule here just kind of to update it, and you can see here, I say next week lab 9 continuation. Hey, should you finish it early, by all means submit it. So it won't be due till your last week, the week that you write. Okay, so on the 27th, you're going to write your final exam. But I'm still going to need a lab from you guys because it's going to take a couple of weeks before we get everything marked and marks posted. I imagine some of you guys may already be working the week after, starting May, right? Those of you that have already gotten employment. So Lab 9 is essentially calculating the properties and writing the report, giving me the job mix formula. In other words, what did we determine? Okay, so I updated this. We're looking at units 3A, 4A, and 5A. Okay, and there's also going to be the calculations of volumetric properties of HRA. Okay, you'll have problems to calculate GSE maybe, GMB, GSB, percent asphalt absorbed, total. Okay, those questions that you see on the assignments are typical things. Okay, so this is the latest one. I don't think I'll have to update it anymore, but if there's any changes, I'll let you know. So, that's coming up. Okay, any questions on the block schedule? Yeah, that's right, Pavel. Sorry, just saw your message here. Yeah, you either multiply by 4 or divide by a quarter. Okay. Let me go to the next one here. Fundamentals of hot mix. If you compare what we've been looking at, asphalt compared to Portland cement concrete, it's quite a bit different. I've always had a love for Portland cement concrete. Asphalt, I find it's okay. I don't mind it. It's very temperamental, very sensitive to fluctuations, to changes. And we'll note that in the lab when we look at some of the properties that we're going to be calculating, and specific gravities come into play. They have a big bearing on the outcome, your VMAs and your air voids. Asphalt, it's used worldwide. It's been around many, many years and successfully too. It's probably a little bit more finicky though. And now when you're talking your asphalts, where you're talking recycled, you're talking polymer additives, it can get pretty hairy. Okay. Some of the key issues here we looked at. We know that it consists of essentially aggregates and asphalt cement. Okay. Mix them together. Just like Portland cement concrete, the water gets absorbed by the aggregates. These aggregates in a hot mix are going to absorb some of the AC, asphalt cement. Okay. I use the acronym AC quite a bit, and you'll notice that even in the notes. If we look at this mix here, you got crushed aggregate, you got the VMAs with some AC, and if you look closer, you can see some small air voids, and that's what you want. And this mix is going to be resistant to movement because it's sharp, it's angular, you got your internal friction, the rough texture, so you're going to have good adhesion between the AC and the aggregate surfaces. So you should have high stability then. Shouldn't have a problem with stability. And even with our mixes here in the city of Winnipeg, all the years that I've been involved with it, stability has never really been an issue. There has never really been a problem with stability. There's other factors that come into play, like air voids and rutting and so forth. Okay. If you look at the mix below it, it's a rough sketch, but it shows you these aggregates are round. They're not sharp, angular ones. And this rough texture, it may not, this is a smooth texture. It may not adhere to the surface as well as it would in the upper sketch. The adjacent mix is formed of rounded particles. They're gonna move around. The combination of interlacking and frictional resistance of the aggregate is termed internal friction. That's when we look at the mix, we say, okay, what's internal friction like? We know that that is key to the performance of the pavement, the hot mix. And we looked at this in your aggregates, and this was part of your quiz, which I'm in the midst of trying to get it finished off, marking. Okay. in order of greatest stability. Fresh particles, rough surface. That's your best. May not always be ideal, may not always be available. So rounded particles, rough surface. You're getting that adhesion. That film of AC is coating the aggregates. At least the rough texture is giving you some adherence. Crushed particles, smooth surface. Okay? You may get the interlock somewhat, but now you're not going to get that adhesion of the film of AC to your aggregates. So you're not going to get that internal friction. And then the worst, obviously, would be rounded particles, smooth surface. We looked at this earlier on. I just want to bring it up again. Aggregates, voids, VMA, voids and mineral aggregate. Add some AC to it, and you're going to get air voids. You're going to get asphalt. This is total, and then you got your aggregate. Keep in mind that some of this asphalt, if you look at our sketch, goes into the aggregate. And that's the absorbed portion. Keep in mind, while I'm here, the final exam, I will provide the formula sheet as part of the exam and the volumetric sketch. So you don't have to worry about it. It'll be there. I mean, you probably have one printed already when you're doing the assignments, maybe. That's fine. But don't worry about trying to download it or whatever. I will have it in the package. It'll be at the back end of the exam. We're shooting for air voids essentially 3 to 5%. It doesn't mean you're going to get 3 to 5% in the field. When you first make a mix and you put it in the field and you pave it, you're probably around 8% air voids in situ. With time and traffic and further compaction, you're going to consolidate, you're going to get it. It's been proven that air voids, from a design point of view, between 3 and 5, you will have the air voids that are required in the field. Now, how much AC? That's always the key. You can have too little, and you're going to suffer on the performance as far as stability. You're going to have more air voids. More air voids is going to be more permeable. It's more permeable, and you get to the seasons where they're wet and then they freeze. Okay, you're going to have the structure that way. So if we looked at a couple of mix, what can happen? Well, we're going to look at these couple of mixes down below here. If you look at this one here, it's a rough sketch. It's not the best artwork, but it says the mix shown below has an excessive amount of asphalt. Okay, due to the high AC content, the aggregates are floating in the mix. The aggregate framework has been destroyed. So in other words, if you add too much AC, it's going to push those particles apart. It's almost similar to Proctor testing. Okay, you guys did standard Proctor last year with Natalie. If you add water past the optimum, it starts to decrease the density because it's pushing the particles away. Whereas when you're first reaching the optimum, it's helping to lubricate and draw the particles together when you're compacting. AC is the same way. Okay, hot mix is the same way. You want to find an optimum AC content that's going to give you the best mix. So if you have too much, you'll have bleeding. And you may have seen that, and I mentioned that. Sometimes when you drive down the highway, you look ahead and you see kind of a glossy patch coming up. And it's excessive amounts of AC or a loss of air voids where the AC bled. Hard to say. Washboarding, rutting, or bleeding may take place in the pavement. Maximum AC and minimum air voids of 2%. And you got to have a minimum. And many times, some of you that may work with MI or other contractors, if you got a 2-lift or a 3-lift construction and your air voids, your VMAs are borderline, you can put them down, depending again on how much borderline, you can put it in the bottom mat. Because you're going to have another mat on top of it, another mat on top of it. typically here we basically have 2 lifts, but I've been on a project where we had 4 lifts. Okay, if you're using sand asphalt, you need thicker layer. And the highway between Winkler and Morden, that was almost an essential sand mix. And that was about 180 to 200 millimeter thick pavement, asphaltic. So again, you can just see it's key. Too much is no good, not enough is no good. The air voids will absorb some of the asphalt cement when the asphalt pavement is subject to traffic loads. That's why we want the air voids. Okay, you gotta have the movement. It's flexible. Okay? So as you're loading those pavements, the air voids are gonna allow movement to a certain degree. That's why we have to be careful on those air voids. The other extreme is where the asphalt cement is added only in sufficient quantity to serve as a binder. And that means you got excessive air voids. So you don't have enough AC. So the voids and mineral aggregates are there based on the aggregates. And if you don't have enough AC, some of it's going to get absorbed. The effective AC now isn't enough. So now you got extreme volume of air voids. It's high permeability. It's conducive to hardening through weathering, oxidation. Brittle pavement mix. There's no flexibility. It's too stiff. It's brittle. So, the maximum should be about 6%. The volume of air void is calculated as a percent of the total volume. It may be expressed as a percentage of the maximum theoretical density. Okay. So that 3 to 5% criteria is what's been proven in the industry to work. That's where we have to be if we're going to have a successful mix. The density you do after compaction, those of you that maybe have done density testing, whether it's on granular base, using those nuclear densometers, or even on the pavement. Typically, you're going to do a percent compaction, and you may do compaction based on the GMM, the maximum theoretical specific gravity, which usually isn't done here. It's usually based on the Marshall density. Just like a proctor. You do a proctor on the A base, you test the density in the field, and the density in the field is what percent of the standard proctor. Same thing here. You compact a hot mix, you do densities on it, either by the nuclear gauge or you take cores, and then you determine what is it based on the stability of that mix. So in other words, you take an asphalt sample, you run stabilities. In other words, you hollowed out the briquettes. You do your bulk specific gravities. You run stabilities, you run flow. Now, everything in the field that was compacted is at what percent of that Marshall density? Okay. Different agencies, some will use different criteria. I believe AMI calls for 97 or 98% of Marshall density. It's been a while since I've read that spec. Okay, the 3 to 5% air criteria is applied to wearing courses only. So in other words, down on the bottom, you can have higher air. But the surface one, where you have a lot of resistance to traffic, that's where you want 3 to 5. Okay. Okay. What are VMA? Well, it represents the space available to accommodate the volume of effective AC. Effective. Because you're going to add total, you're going to lose some of it into the aggregate. It's going to be absorbed. So the remaining is the effective. So the voids filled with AC is your effective asphalt content. Same thing. So your VBE, the volume of effective bitumen, is also the voids filled with asphalt. Makes sense, right? One size aggregate may have a high VMA. It may be as high as 35% or more. A well-graded aggregate has a VMA below 20. That's why we're running 6 to 16. Well-graded aggregates without an excessive amount of fines will produce a VMA of about 15%. Okay, we're shooting 6 to 16, so we're in that range. And our mix, our passing 0.075 millimeters for the blended aggregates, we were shooting for 5.4, 5.2, 5.3%. Excessively low. It's not high. Asphalt pavements with low VMA do not perform well in the field. So it's critical. You got to have that optimum void and mineral aggregate. That's a starting point. Questions so far? Okay. We've been talking voids, we've been talking voids, we've been talking voids. And what are they dependent on? These three things. The surface area and size of your aggregate, the roughness, and obviously its absorption. If you have high absorptive aggregates and you haven't designed it properly and your AC content is low, you're going to lose a lot of it into the aggregates and you're not going to have your effective AC content. Okay, so it's key. A couple of things here to remember. Again, it's based on surface area. Optimum AC content is greater for mixes containing well-graded aggregate with small top size. Okay, maximum size is low, smaller. That means your grading is finer. The larger aggregate, because a greater quantity of small size particles will have a larger surface area. You know, sand has more surface area than gravel, and coarse aggregate. That's why in Portland cement concrete, if you have a very sandy mix, you need more water to make it workable because you need more cement because of the greater surface area. The asphalt absorption and or the percentage of aggregate fines have much more influence on the optimum AC than the aggregate top size. The mix will require a high AC to compensate for the absorbed asphalt cement, right? Or surface area, greater absorption. The amount of fines in the aggregate, especially smaller than 2 millimeters, will impact your optimum AC content. So in other words, a mix, for example, with more material passing 425 will have a higher optimum AC than a mix with a larger top size, which of course, you just kind of reread that a few times to kind of get that straight in your head. I made it yellow for a reason. Okay. There's a lot of information coming up here now, and again, this comes with experience in it. I'm going to just highlight some key issues. I don't expect you to know it all. It takes a good understanding of asphalt technology to work with this, but some of it definitely is pretty straightforward. We've had properties that we're trying to achieve: VMAs, air voids, stability. Again, stability is the resistance to movement. How strong is that pavement? How flexible is it? You may have high stabilities. Okay, I believe we need 7,000 newtons, City of Winnipeg. You may be 10, 11. Is that a good mix? May not be. Maybe it's too high. It's not flexible enough. It's too brittle, possibly. So there's a rhyme or reason why we select certain criteria. So if you have low stability, we can have low stability. What are some of the causes? Well, too much asphalt. Okay, that's why we got to get that optimum. Remember, we're looking for well-graded mixes. Maybe you've got too much sand in there, the medium-sized sand, okay? And one of the key factors we know, internal friction, is key for stability. Maybe our aggregates are out. Maybe we're using too many rounded That's why we got to do crush counts on them. So these are some key issues. So low stability, well, if you have too much AC, you'll know that sometimes you'll get bleeding, you'll get rutting. How many people have noticed a few years ago, if you travel the west perimeter, coming up to McGillivray, okay, you're coming from the south and you're heading north, west and then north on the perimeter, and you pull up to the lights at McGillivray there by the Humphreys station there, gas station. Just before you hit those lights, it was very obvious you had real deep ruts in the pavement. Okay, and that's accessory where you're taking off or you're putting your binders on, you're slowing down. You're having a problem there. There's low stability, and it may have been caused by IACs. And if that's the case, then you've got bleeding. So washboarding, rutting, and flushing or bleeding is the effects if you have too much AC in the mix. If you have too much sand, it's tender during rolling, and you'll notice that when you're compacting it. Well-graded aggregate compacts well. Uniform, one size, two size aggregate doesn't. We know that from granular base compaction. You know, you place the hot mix, you got your breakdown roller going in, and we'll be looking at that the next class on some construction practices. The guy on that breakdown roller, if the mix is too tender, sometimes he's got to back off because it's too warm. Whereas the mix was well graded, you could follow that paver maybe fairly close. Tenderness during rolling and or period after construction. And it's difficult in compacting. It kind of just ravels in front, okay? It's pushing out. So too much fines. Too much fine aggregate, not too much fines. And obviously, if your stability is low, is because of internal friction isn't there, you don't have those crushed aggregates, you're going to have rutting and channeling. We also know if we have low stability, durability may be in question. So poor durability. What causes poor durability? Low AC. High voids. Now that is a design. Lack of compaction is a construction problem. But if the design is off, compaction may be off accordingly. So you can have a lack of compaction by having an inexperienced contractor, or it's dependent on the mix characteristics. You can only do so much with it as far as compaction. And obviously, you have poor durability. You're going to have hydrophilic aggregates. It's going to be susceptible. And those are the causes, and these are the effects, okay? Mix to permeable. Low AC. High air voids. Could be a design thing. Inadequate compaction. Your mix design, it's like concrete, can be ideal. If you don't place it properly, inexperienced workmanship, whatever the case may be, that's going to add. You come up with a good design, you come up with a good mix, but what you do with it is another question. Typically, the designers, many times, are not the contractors that are placing it. Low AC content, well, you're going to have thin film. Your effective AC is going to be low. If you have high voids, you're going to have oxidation, you've got water and air. So water goes in, it freezes. High air, you're going to get oxidation with time. And obviously with inadequate compaction, same thing, you're going to get high air voids, which will lead to greater permeability, low strength. Poor workability. Poor fatigue. Fatigue comes with time, workability. Now, this is more of a problem with the contractor. You can design a mix possibly to give you exactly what you want, the best. But if you can't place it, can't compact it. So, you know, are you any better off? No. It's like Portland cement concrete. If you can't place it and finish it, if it's too stiff, what good is it? So you got to design so that mix can perform in the field. Well, workability. Now, this is essentially a mix design issue. Large maximum size particles, maybe too much coarse. Key temperatures. Those of you that may have worked on a paving project, you've got to make sure that that temperature, when it arrives on the job on the construction site, probably, it's got to be there so you can place it and compact it and get those densities before it cools off. For workability, again, it's grading. Minus 200 content. Okay. Or skid. Excess asphalt. You get bleeding, flushing. You got that slick AC on the surface, you're going to be sliding. And again, that's why we need the rough textured crushed aggregate. Not only are we getting that internal friction, we're also getting resistance to slippage. And rounded aggregates, they're polished. It's going to give us poor skid resistance. Poorly textured or graded aggregate, polishing aggregate, essentially the same thing. If it's poorly textured, chances are it's polishing. So here, we're in the mixture, we're going to have low skid resistance. Here, though, on wet conditions, you're prone to hydroplaning. Okay, any questions so far? I'm going through this fairly quickly for the simple reason some of this was covered in our aggregates, but criteria for a satisfactory paving mix. Here's some Marshall design criteria that's taken out of Asphalt Institute, and you'll see this quite a bit. And you'll see that in all other agencies. And you look at the light traffic, when you're designing a pavement, the thickness of the pavement is going to be dependent on the magnitude of traffic and the frequency. And we took that in Unit 1 when we first got into concrete portion, the Portland cement concrete. It's the magnitude of those loads and also the frequency. And they refer to that by counting the number of single axle loads, the equivalent. If we do pavement thickness design, you would cover that. So you're looking at light traffic, medium traffic, and heavy traffic. And City of Winnipeg, we're in the heavy traffic because we do have arterial roads, we've got our residential roads, but we also have roads that will take Main Street, Portage. The bigger arterial roads will take a lot more heavy truck traffic. So here we go with 75 blows of compaction. Okay, the video where you drop hammer, 75 blows on one face, pull out the mold, flip it over, pack 75 on the other side. So we're using a lot more energy. So if we're using a lot more energy, our densities are going to be greater. We're looking at stability. Typically, you would be looking at newtons of about 8,000. We're 7, I believe, for City of Winnipeg. Are we not? Can't remember. Flow, we're between 6 and 16. Here, they're going between 8 and 14. Okay. And the voids, here we are, 3 to 5. So you can see here that our VMA changes somewhat for the simple reason they just put a footnote for the VMA. That's going to be dependent on your maximum size. So if you look at number 6 here, percent voids and mineral aggregate. Percent voids and the mineral aggregates will be calculated on the basis of the bulk specific gravity of the aggregate. So it's a function of the aggregate. But anyhow, so here you can see that there's different criteria based on your traffic loading, light traffic, medium, and you have a range, 75, 75, and so forth, okay? Under no circumstances shall the allowable flow value be exceeded, or shall the stability value be less than that required. What they're mentioning here is economics comes into play, and sometimes it may be cheaper. But if you're making a cheaper mix and you're sacrificing your flow and your stability, high flows are not good because you're going to have too much deformation. Low flows are no good because your pavement's too brittle. It's not flexible enough. So you've got to have a happy medium. Mixes with abnormally high values of Marshall stability and abnormally low flow values are often less desirable because pavements of such mixes tend to be more rigid or brittle and may crack under heavy volumes of traffic. We know if something is very, very brittle, there's no ductility to it. It can't bend. Stress strain. You have a material where your load may be low, but your strain may be high, so there's more flexibility. A weak silk, for example, if you did an unconfined compression strength test, you have low loading but phenomenal strains. So this was taken out of Asphalt Institute. And this just gives you the minimum percent voids in a mineral aggregate. But that should have been down in the next one. Here's the typical one we're looking at. Okay, this is essentially what's happening in a hot mix. You've got aggregate, you've got absorbed portion, and this is your effective. In other words, your VMA is from there to there. You've got air voids. Here's your voids filled with asphalt, which is your effective. VBE, volume of effective bitumen, is equal to the volume of voids filled with asphalt. Okay, straightforward. We have an effective volume of aggregates, and that's this one here. That's this one without the aggregate that contains the asphalt. In other words, the voids containing the asphalt. Here's your total AC. It's made up of voids filled with asphalt and what got absorbed. Okay, sorry, what got absorbed here? This way. Here's your maximum density, specific gravity, VMM. You can see there's no air voids. Add the air voids to it and you get your bulk. Knowing these specific gravities, you can determine volumes. Given a mass, you can determine. We went over that on the volumetric calculation, that PowerPoint, but I believe it's a PDF copy for you guys. Formulas are given on the bottom here, straightforward. Keep in mind, some of you that have done that assignment, there's one problem there where you have to calculate GSE. You have to calculate GMM. Well, you're saying, if I look at my formula here for effective specific gravity, I have to know my GMM. So you say, well, I'm going to calculate my GMM. So I'm going to calculate my GMM, but I got to know my GSE. Now what do I do? Look at all the other formulas. It'll come. Okay. If you know the absorption, and you know the bulk specific gravity of the aggregate, you know the specific gravity of the AC or the bitumen, you can calculate GSE. You calculate GSE. Okay. Plug it in here and calculate GMM, then you go back here. Whatever. Okay. So these are the formulas given to you. Now, I've uploaded a PDF copy on the Marshall Mix Design. It's a PowerPoint slide. I believe it's in PDF format. It gives you essentially the step-by-step procedure that we would have been doing physically had we had face-to-face labs. I'm going to go over just some key issues here to mention the requirements that leads you up to. We got to select the aggregate gradation. We've done that. And we have to determine the optimum AC. That's essentially what we're trying to do. Is we've got aggregate, we got to find the optimum blend, and then we got to find the optimum AC to mix with that aggregate to give us the physical properties that we're looking at. And there were many methods done. The Hubbard, the Marshall, the Chavim, surface area. This is the one that's now widely used all over the place, except here in Manitoba. Essentially, we've always been doing the Marshall. And Bruce Marshall, who was an engineer way back, I think, in the 30s with the Mississippi Department of Highways, he came up with the whole concept of Marshall Mix Designs. Hence his name, hence the name Marshall Mix Design, after Bruce Marshall. I think in the video that Ray put together, he had shown you viscosity, temperature viscosity chart. These charts are required to determine at what temperature do I mix my mix. I gotta heat my AC, I gotta heat my aggregate, I gotta blend them, I gotta mix it at a certain temperature. What temperature is it? Well, it's a function of your asphalt cement, the AC. And then I gotta have a certain temperature to compact it. If it's too cold, I won't get my density. If it's too hot, I'll get higher densities and I'll suffer on my air voids. So there's an optimum. So what they do is they run viscosity tests. And there's criteria that they select for the viscosity, and they join the two lines together. So when you have a chart, the mixing and compacting temperatures are determined from the temperature viscosity chart. The temperature of those required to produce viscosities of 170 plus or minus 12, plus 20 centistokes, and 280 plus 30 centistokes for compacting. Don't worry, you don't have to know those things. I just want you to understand how we get these temperatures. We get them from a temperature viscosity chart. So if you look here, you come across, okay, there's your viscosities you come across, and then you come down. So I'm at 147 to 152, my compaction range. For mixing range, say 157 down to 62. So that's the range. So that's where it's key. It's based on those viscosities of the AC. So you would run, and these charts are usually provided, or they should always be provided, by your AC supplier, whether it's Husky, whether it's Esso, or Petro-Canada still in there. Anyhow, so this is what we use to compact those briquettes. And we compact briquettes. And the density of the briquettes are measured to calculate the voids. So these briquettes, we can do percent voids, percent VMA, and percent voids filled with asphalt, which is just a function of the VMA. Okay? So those briquettes give us enough information. From those briquettes, to get percent voids, to get VMA, to get voids filled with AC, we have to determine its bulk density. Weight in air, weight in water. Straightforward. No different than aggregate. No different than the AC when you're doing your GMM, except you're doing it in a container. But these voids, it's the same thing. You would put it in a basket. Mass of water is your volume, water displacement. It tells you how to do it. Briquettes, that's straightforward. I'm not going to go through it. That's a lab procedure. Select the optimum, and this is going to come up again in the lab. Remember we said the selected design air void is essentially the medium of the air void range. So we're 3 to 5, so we're looking at 4%. Or any chosen. I mean, you may be with a different agency, different mix, whatever. You typically look at the maximum stability and the bulk density. But the key governing one is 4%, because your maximum stability does have a spec range on it. So you want to make sure that you also have you're within that maximum stability, you're below it. Density is going to be a function of the mix, so there's no criteria really for density. So AC, you select 4%. What's my AC at 4% air voids? And you start from there. Okay. I mentioned when you're producing asphalt, you can look at the AC content as percent of total mix, which is what the city of Winnipeg does. Asphalt Institute does. A lot of agencies do. Highways, they design AC content percent of aggregate, almost like moisture content. So here, for an example, if you had 1,200 grams of aggregate and you had 60 grams of AC that you were blending to it, based on mass of dry aggregate, you've got an AC content of 5%. But if you do it mass of total mix, 4.76%. They're both acceptable as long as you know how it's been designed. So when you're calibrating a plant for MI, he's got to calibrate it. He's got to calibrate his AC based on total mix or total aggregate, whatever the case may be. So it's got to be always specified as to what the design is. So it just goes to show you you're out 0.25% just about, just from looking at it differently. Now, these are the graphs that we're going to be looking at. These are very crude in that they're hard to read, but there's other ones we'll be looking at in your lab. This is what we're after. When we calculate these physical properties at 4% AC, at 4.5% AC, 5% AC, 5.5% AC, 6%, 6.5%. We've done a fair amount. For the simple reason is because we had 6 groups of lab groups. In the real world, you might say, okay, my AC optimum from past experience is about 5%, 5.2, 5.25. So I'm going to do 4.5, 5, and 5.5. In other words, you want to be on both sides of optimum, just like when you're doing a Proctor test. The more you have, the better off your curve, because sometimes your data isn't good. And you can see here the shape of these curves, and they're typical. I put up 2 examples in Learn. One's from the Asphalt Institute, and the other one is also from one from NAPA, I believe, National Asphalt Paving Association. But anyhow, they're typical, and these are typical. But keep in mind, see these data points? You're not going to have them that pretty. You may have them all over the place. When I mean all over the place, obviously you're going to have outliers, but you may have a little bit on each side of it. So these are the best fit. So you always make sure, and we'll go over this more in the lab, that you plot the relationship, the trend. Don't join every point. It's not right. You're going to have erratic results. We know that that's the shape of those curves. Here, for example, air voids versus AC. You can see with an increase in AC, and as AC increases, your air voids drop. Okay, so you're getting a parabolic or somewhat of a parabolic 1.5 curve here. Okay, air voids are high. As the AC increases, air voids decrease. Same with stability. Same with flow. Density. These are some things to consider, and I've actually elaborated in Lab 9. I've got the job mix for report requirements. There's this section here. Sorry. These have been all elaborated in a little bit more. Okay. So I'll look at that later. The VMA should remain constant within the mix design, except for a slight dip at the optimum AC content. The aggregates are carefully measured so that the gradation is the same for each point. So it follows that the structure would remain the same within 0.1, 0.2%. The asphalt absorption should also remain the same for each AC because the gradation is the same. Makes sense. If you've got your aggregate consistent, The gradation's consistent. The batching is consistent. Aggregate absorption is aggregate absorption. It should be the same. Doesn't matter whether you're adding 4% AC to it or 5% AC to it or 6%. The absorption as a percent is going to be the same. Aggregates are aggregates. Now, if your aggregates vary, and this is what we're going to look at later in the lab, specific gravities of aggregate are very important when it comes to void calculations. You can have two aggregates, two blended aggregates, same gradation. Their specific gravities can be different. Okay? A change, that's why typically a change of 0.2 on a specific gravity can change your air voids and VMAs considerably. So you've got the same top size, you've got the same grading, specific gravities are different, different aggregate types. That's why you've read in the specification that when a contractor chooses to change the source of aggregates, another mix design has to be done. Because if those specific gravities aren't the same, or if you're using two coarse specific gravities and they differ within the blend, they differ quite a bit, it's going to affect it. So gradation is one thing. We know that gradation gives us optimum compaction, a well-graded mix. But like I say, you're going to have two well-graded mixes. If the specific gravities on those aggregates are different, you're going to have different. And when we go to our lab, I'm going to explain something. Those of you that may have looked at that spreadsheet that I put up there, I gave you specific gravity, bulk specific gravity of the aggregate. I think it's group 1 of 2.593. And that was determined from that optimum blend that I provided when I was marking your labs. I said this percentage of blends is closer to the target. So that specific gravity, bulk specific gravity of the aggregate, 2.593, is actually a little on the low side. But if we went to lab 6 and you took the individual specific gravities, each aggregate, and then based on the percentages of each aggregate using the blend, you're going to get it weighted. Because the coarse aggregate, I believe, was like 2.665 or 4. The sands were in the 2.5 range. So the blended ended up 2.59. But we'll go over that. So I just want to stress the point that specific gravities are key for calculating your voids. Even though gradations may be the same. Gradations will give you your compaction capabilities, your friction, your internal. The maximum theoretical specific gravity of a mix is the specific gravity of the mix without air voids. It's used in the calculation of air voids, asphalt absorption, VMA. Value can significantly affect the accuracy of determining the air voids in the compacted mix. Therefore, extreme care is to be used in determining maximum theoretical density, specific gravity, whatever you call it. Okay? And that's why we calculate the 3 decimal places. Round to 2, by rounding off, it can affect the results. So when we're looking at specific gravities for aggregates, when we're looking at it for the bulk specific gravity of a mix, if we're looking at it for the maximum theoretical specific gravity of the mix, take it to 3 decimal places. 4 significant figures. Not 3, not 2. Because then your calculations of your voids are going to be all. This is the procedure of doing the bulk specific gravity. While we've covered that in our other labs. Gives you definition of asphalt absorption. Just the reinforcement of our formulas. You have these formulas on the formula sheet. And again, here's be an example, but we'll look at this a little bit more in our lab. Essentially, you have 5 AC contents here, okay? And calculate the briquettes, the density, the stability, and the flow. And you would plot them on those graphs. Anyhow, let's leave it here. That is just the fundamentals. When we're talking about, like I said, there's a fair amount of information to know here about some of the, I'll try and ensure that the importance is the poor skid resistance. Okay. Poor fatigue, I'm not going to worry too much about the causes of it, but these are some of the problems with the mix. There's usually a cause and an effect, but no the poor skid resistance, no poor fatigue resistance, poor workability, okay, that's important. Permeable, durability, low stability, okay. I'm not going to give you a lot of questions on them, but I may give you a true and false, or ask for what might be for low stability. Give me two causes for low stability. Okay. Keep in mind, we're covering the next unit, which is going to be construction, placements and procedures and compaction. So 3 hours, I can't cover too much, but I want to definitely cover the properties, calculation of the volumetrics. You might have 2, 3 questions on that. I'm not sure. Okay. Let's take a little bit of a break here. No, Pavel, they're not linear trend lines. We'll discuss that in the labs. There's a slight curvature for most of them. So I usually use the polynomial curvature. They're not linear, especially if you look at a lot of graphs, stability, if you look at graphs on your density, okay, curves. They're not linear. AC, it sometimes looks linear, but there's a slight curve to it, okay? From the upper left-hand corner curving down and to the right, bottom right, okay? We'll look at them in the next go around here when we're doing our lab. Okay, let's take, it's 10:12. Let's come back at 10:20 or 10:25. Have a coffee. We'll look into the lab, and I want to go over that spreadsheet that I put up there and how we're going to fill it out. In the past, we've always relied on other groups to calculate their AC content and give the results to everybody else. However, there are always some groups that are way late and it's holding everybody up. So what I may do is I may have each group calculate all, the 4, the 4.5, the 5, the 5. But we'll discuss that when after coffee break. Okay, any questions on the fundamentals of AC? Okay, let's take a little bit of a break. I'll just pause the recording and we'll come right back to you at say 10:25. Okay. Hey, we're back. I resumed the recording again. So, okay. The lab 9 now. We want to come up with our job mix formula. This is all that. When a physical mix design is put together, there's a lot of work involved. And that's why a lot of the testing agencies, they charge a pretty penny for it because there is a lot of work. It's very labor intensive. You have technicians, you may have one working on it, you may have two working on it. And depending on the aggregates and the information that they have on the aggregates. Essentially, you're starting right from square one. Gradations, specific gravity testing on the aggregates. Okay? A lot of these values we were given as virtual data. But in the real world, you actually physically got to go through it. The specific gravity on the aggregates and so forth. Okay, lab 9, I'm going to look at the criteria that we want for it. I'm going to start sharing it here. I'm going to show a couple of curves and so forth. We'll go through all the procedures and the requirements. Let's Excel, we'll come here. Okay. Do you see that okay? Lab 9 requirements. Okay, we're gonna, like I said earlier, lab 9 and 10 are combined. Lab 9 was essentially calculating the volumetrics, calculating the air voids, the VMA, asphalt absorption, the total, the effective, and so forth. We're going to do that, and then you're also going to plot the results, and from that you're going to be able to determine the job mix formula. Probably better to do it that way because everything's fresh in your mind. And technical lab. The content should have a commentary, a summary page. In other words, you're going to have your data, have your spreadsheet, you're going to have your graphs, and then your report is going to comment on that. It's going to comment on your graphing and the interpretation. For attachments, please include the spreadsheet of all the physical properties determined for each of the AC contents and include all the 6 graphs that are used to determine the job mix formula. The voids filled with asphalt is not used, but we still show it. It's a good indication. It's just the opposite of the air voids. Typical plots of the results showing the trends and relations are uploaded into the Learn Lab folder. The typical test property curves have been found to follow a reasonably consistent pattern for dense graded paving mixes. Variations do occur, and they will occur. But the trends from past experience will help you plot because you may have some erratic points. When I mean erratic, not nicely on the curve. But there's things to look forward to that's going to help you guide the shape of the curve. And let's have a look at one of the curves here, for example. And this is one of them. And they're only showing the 5, but now keep in mind, these are taken from industry. We're way up in here. We're between 4 to 6. And our AC content is going to be roughly around 5.2, 5.3 from past experience. But this gives you an idea. You can change the scales to match your mix. That's not the problem. But you can see here, air voids. As the AC increases, the air voids decrease. If you kept adding more and more AC, eventually you'd have 0 air voids. They're bleeding. So you can see here, it's not this one, if any of them, is more linear than all the rest. But I use a polynomial because sometimes you'll have a point up here, you may have a point down here, whatever. That's why it's very important that the accuracy of these tests are done. So here you have the AC plotted versus air voids. Here we're plotting AC content versus VMA. And a lot of people, what they do is they put these one above each other. So that way you can just come down. If you say at 4%, for example, the median between 3% and 5% air voids, we select our optimum AC that gives us the median air void, which is 4. So for this example only, if you come across here and it intersects, you're at about 4.7. So that's a starting point. Do all the other physical properties meet at 4.7? We have to look. So you would look at 4.7. The VMA here is under 14. I believe we have to have a minimum 14, right? So it doesn't meet. And again, low VMA is our problem. Okay, 4.7. What's our voids filled? Well, that's going to be a function. So we're looking at about 70% of the VMA are filled with AC. Stability. If you start earlier here, it's almost like a Proctor curve. But here you can see on the downswing. So at 4.7, they've got a stability of 2,300 pounds. Again, unfortunately, this is not in metric, it's imperial. So whatever 2,300 converts to in newtons. But you would then see, does it meet my minimum 7,000? I think the city has. And flow, 4.7. They're at 9. Okay, and in this case, it's units of 0.01 because it's imperial. We're units of 0.25. But this gives you the trend, the relationship, the shape of those curves. I've seen people have this go this way. Sorry. That's wrong. It's got to be these shapes. They won't be, maybe not be as pretty. You may have some variation, but you do the best fit. And you can see the VMA, you've got at lower AC contents, you have higher air voids. Sorry, VMA, voids and mineral aggregates, which makes sense. As you're adding the AC, it's drawing them closer and closer together. Okay, so you're reducing the voids. It's almost the reverse of a proctor. Remember, the proctor goes, this is reverse. You keep adding AC, and now it's pushing the aggregates apart. So after an optimum AC content, it's going to start going up. So it's almost like the bowl, concave, soup bowl, bottom of your soup bowl. Voids filled with asphalt. Now flow will always increase if your AC increases. And here you can see they got boom, 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 and that can happen. I've seen it. This is the shape of the curve. It's got to be. Can't go the other way. Increase in AC content, increase in flow. Just makes sense. Stability, same thing. Increase in AC content, stability goes up for a while, reaches optimum, then it drops. They're on the back end of the curve here. So these gives you an idea what the curves look like. There was another one I loaded up on Learn. Okay. So stability values increase as AC content up to a maximum, then decreases. Flow value consistently increases with increasing AC content. Density curve of total mix follows the trend similar to the stability, except that the maximum density, normally but not always, occurs at a slightly higher AC. Percent air voids steadily decrease with increase in AC content. Percent VMA generally decreases due to better compaction to a minimum value, and then increases with increasing AC content because the aggregates are starting to be pushed apart. Excess AC. And the percent voids filled with asphalt steadily increases with increasing AC content because you're filling the VMAs. Or AC, the more of the VMAs are being filled with the AC, which will give you lower air voids, but this goes. So the VFA increases. The data points at times may be such that the typical shape of the curve for a specific property may not be ideal. However, plot all your data points. Do not remove them. You plot them as you see them. And then plot a best fit line, trend line. You can do these manually if you want. I've seen industry use the program to plot the points, but they don't put the line in. They'll print them, and then the technician will physically draw the best fit. There's a way of doing it with an Excel, and I'll give you some pointers here. Plot all the data points, and then plot a best fit line or trend line. Keep in mind that Excel will use all the data points for a best fit, and the resulting plot may still not be a typical plot. Okay, you're not using the Excel line. There's no line because it'll just, okay. So what you do then is you plot the markers, no line, and then put a trend line in. But the trend line is going to read all the points and take the best fit, and still may give you somewhat of a wonky, not ideal curve. So then what you do is you do another series. And your X and Y axis, you select only those points in series 2, only the AC contents and the corresponding air void or whatever you're plotting, and put the trend line to those points only. And you can change the marker color to match series 1. So what you're really doing is you've got 2 series data points. The trend line for it is wonky, so you remove it. You do another series, you plot. You don't really plot them, but you tell it to read it, which you will plot, but then you use the same marker color. And then the trend line number 2 will only pick up those and fit them in. Keep in mind that Excel will use all the data points for a best fit, and the resulting plot may still not be a typical plot. This is where we may need to unselect some data points for a new trend line. Do not leave out the data points. We select the points we want in a new series for Excel to read and base the new trend line on. Or those of you that have printers, you want to print it and pencil it in, nice curve, use a French curve, no freehand, you gotta have nice curves. You do that. Based on the graphs, select the optimum AC content that results in the required physical properties meeting the City Winnipeg specs for Type 1A mix. We want to come up with an AC content that's going to meet all the properties. But we select the optimum at 4% air voids. That's a starting point. The Asphalt Institute recommends choosing AC content at the median of the percent air voids limits, which is 4%. If all the other properties meet the city specs, then this is the optimum AC content. If you have to select an AC content at an air void content a little less or a little more than 4% just to meet all the specs, then that's fine. So you're selecting a 3.9 or 4.1. Let's say at 4.1 they're all in spec, but at 4 they're not. Pick 4.1. We're starting at 4. You don't want to have 4.9. You don't want to have 3.1 as your optimum because you're too close to those limits, minimum and maximum, and you're going to fall out. Keep in mind that we don't want to be on the low or high ends of the air voids. If some of the properties are not met, state a conclusion or recommendation as to the acceptance or rejection of the job mix formula, and if remedial measures can be implemented. Now, I put that in for a reason, and we're going to look at something here right away. I had mentioned that I had given you 2.593 as the blended gradation specific gravity based on that target gradation. Okay, for group 1 and group 2, there is a recommended blend that's going to get you as close to that target as possible. And I put that on your reports. So if we go to that spreadsheet, just going to pull one of them up. Okay. You can see here 2.593. This is the bulk specific gravity of the aggregate based on that blend. I don't have it quite handy for group 1. Group 2's was a little bit different. So the bulk specific gravity is 2.593. You calculated GMM, GMB, stability, and flow. You calculated these in the last lab. I will pencil them in once I get your labs. So in other words, then you have to calculate the effective specific gravity. I will give you bulk specific gravity of the AC. I should have given that to you now, but it'll be 1.028. Your actual percent AC. We're designing for 4, but what's the actual? How would you calculate the actual? Anybody? Okay, how do you calculate your actual? We're designing for 4. Are we at 4? Are we at 4.5? Are we at 5? Remember in that mix design video? You got your aggregates, they're heated, you put them on the scale, you weigh them, you figure out, okay, I'm at this point that I'm compacting, these briquettes are going to be at 4%. I got to add a certain amount to it, right? What happens if you overshoot it? So are you at 5%? So how would we calculate this? Look at what I gave you guys. Anybody? Yell it out if you have to.
Either you could do a burn off, or if you know how much aggregate you had, you can just weigh the whole mix together to figure out how much bituminous material you had.
Right, but yeah, and it's not a burn off, it's an extraction test, guys. You and your burn offs. MI's term for it.
Industry term, sorry.
That's okay. I know what it's meant. Because before that, we used to extract it with a centrifuge using trichloroethylene. So they weren't burn offs. But anyhow, well, yeah, that's how you physically determine a mix. But on this spreadsheet, right now, could you calculate the actual asphalt content? Anybody? How do you calculate percent AC of total mix? Hello? Guys awake? Sleeping? Come on.
Divide the mass of the asphalt that you put in divided by the total weight of the mix.
Right. And can you determine that from the spreadsheet for the information I just gave you right now?
Well, we have 50.3 grams of asphalt divided by 1,250 to 53.2.
Exactly. Got it. Now, I'm not saying that maybe that works out to 4.0, but maybe 4.5, maybe it works out to a little bit different. When I'm calculating the other ones here, because when you're calculating, this is the AC you're going to use in your calculations, not this one. This is design. This is the actual, because the mix was compacted with 50.3 grams of AC and 1,202.9 grams of aggregate. That AC is what it works out to be. It's not 4. It might be. I don't know. I haven't gone through this. Might be 5. Might be 5.5. So this is the PB, percent bitumen. That's what you're going to use in your calculations of absorbed asphalt, PBA. The effective percent GMB is what your lab 8 is right now. You're calculating GMB, you're calculating GMM, you're calculating stability, you're calculating flow. Okay? So what I've done in the past is when we physically compact these, group 1A would be compacting 3 briquettes and 1 mixture for GMM, 4%. Group 1B did 4.5 in car C. Group 1C did 5. 1D did 5.5. Then everybody calculates their own. And then group 1A sends me their results. Group 1B sends me the results. Group 1C sends me, and so forth. And then I put them on a spreadsheet. I fill all this out. And then I send it back into Learn, and then you guys plot everything. But I have to really lean on some lab groups because they were late, holding everybody up. I can still do that again. Or I can say, you know, guys, every group calculates all the properties. So in other words, group 1A is going to calculate all these empties. Group 1B calculates all it. And then you're not relying on anybody. Okay, now I know your plate's full. Most people I know, you guys are pretty efficient with Excel. I mean, once you put one formula into a spreadsheet, if you're setting up a spreadsheet, then you copy that formula, it'll calculate most things for you here. Once you get your formulas in there, that's where your formula sheet comes in, okay? So we can do with that, then you're not depending. In other words, you're not, 1A is not waiting for 1F because 1F is out gallivanting or having parties or whatever, not doing the work, okay? So maybe that's the way to go. That way you're not relying on everybody. So with this in mind, okay, I'm going to send another one this afternoon. Okay. Now I know what your calculated GMBs and GMMs should be. Because when I gave you that data, I also calculated. So I know that when you submit your lab today, at 10 o'clock at night, I know what these should be. If they're not, then you've obviously made a calculation error. So I will put what they should be in there. Okay? But remember that comment I said? If the mix doesn't meet specifications, you have to give me a recommendation or a conclusion. Tell me this mix design does not meet at any AC content. And the reason for that is I want to show you something here. Okay, so anyways, this is what you're going to be having essentially. I'm going to update this one and we'll put in the data that is required. Any questions so far? Like each one of these, I will also, I'll give you the specific gravity, sorry. That's 1.028, but I'll put that in. Remember bulk density? It's GMB times 997.0, which is the density of water at what temperature? Okay, so you're going to be slightly lower than your GMB. When we're talking metric, we're talking specific gravities, 1 gram per cubic centimeter. The numbers, numerically, the numbers are the same, except one has units, one doesn't. That's the beauty of being in metric. If we were imperial and you read some of the literature in ASTM and that, the density of water, does anybody know what the density of water is in imperial? Okay, we know it's 1 gram per cubic centimeter. It's 1,000 kgs per cubic meter. What's the density of water if we're talking imperial? So 62.4 pounds a cubic foot. That's the density of water. So instead of multiplying by 1 or 1,000, you got to multiply everything to convert to density. 62.4 pounds a cubic foot. Gallon of water is 10 pounds, and you can figure out from there. But anyways, so this is the beauty. So we know that this bulk density in kilograms per cubic meter, numerically, it should be less than GMB because we're multiplying by 997 here, kilograms per cubic meter, not 1,000. 1.94 slugs, you got her, Fabian. You remember that in those geotechnical notes, eh? I got to remove them. Natalie never removed it, eh? Slugs. I don't really got that one. It's almost like so many stones, masses and so many stones. A horse is so many hands high. Excuse me. Anybody know what a kip is? I took the course, we were working in kips. 1,000 pounds. Okay. Pounds per square foot. Kips per square foot when you're doing stresses. Anyhow. Okay. Brings me to, stop sharing this one. I have an Excel spreadsheet here I want to use. Okay. This is an example how it's going to be filled out. But here's the 2.593 that I gave you. Okay. And these are the GMBs, GMMs. Quit taking pictures, guys. Calculate that on your own because maybe I'm pulling your leg and maybe they're wrong. Calculate them. Don't take me as being correct because I'm not correct that often. There's the stabilities. What do we record stability to? Flow. Okay. Yeah, that's right, Graham. Okay. Now, you would go through all these calculations. You might have the formulas in there. For example, you may have airplanes, AMAs, and then you just copy those formulas. What does that look like if you plot it? Okay. Air voids versus asphalt cement. You can see that they don't always fall on the curve. In this case, they did. Fairly reasonable. You can plot it. Your VMA Again, you plot VMA versus AC content. Stability, it's kind of like a Proctor curve, but sometimes you, depending on where you are in your AC, you may only be back in here. Flow, you can see flow is really erratic in most instances, but it's a general trend upwards. As the AC content increases, flow's got to increase. Can't become stiffer. Density, function again. You keep adding AC, density goes up and up until the optimum is reached and comes down. And then the voids filled with asphalt is just, as it increases, the VMA gets filled with the effective AC. You got an excess amount. Now, if you look at this curve, that's starting point, 4%. Okay, come across, come across, come across, come across. And I'm about 5.2. Okay, 5.2, there's my stability. I think our stability was what, 7,000? We're way above, way above. Density is going to be what it's going to be at 5.2. There's no spec on it. Voids filled with asphalt as a function of the VMA. So at 5.2, you got about 72% of the VMAs are filled with asphalt. At 5.2, your flow is 14. You're okay. But look at here. 5.2. What's our VMA? Ready? Chat up here. Hold on. Okay. What can you tell me about the VMA? What do we need? Well, guys, you should know the city spec by now. I'm looking at it for aggregates and everything else. Somebody please help me. What's our minimum VMA that we need? Hello?
I think it's 14.
14. Thanks, Fabian. Are we in spec anywhere?
Between 4 and 5%.
Right. But what's our specification for AC content in the city of Winnipeg spec? 5 to 6. We have a severe problem here. We've got a mix design where VMA doesn't meet. I mean, even if you went here, let's say I'm going to use 4.95. Well, if you came here at 4.95, you'd be very close to being out on your air voids, which is critical. So what would you do in this case?
Pick 5.
6.5, but what about your AC? What's the limits for AC content?
I meant pick 5%, not 6.5. Sorry.
6.5. You're talking about your AC 6.5 or?
AC at 5%.
Oh, at
Pretty close
5%.
to 14.
Right.
And see if it meets all the other properties.
Yeah, come on. Stability, it does. Density is a function. That's a function. Flow, it does. But would you recommend this mix? If you're batching at 5%, what's the chance of you being at a spec below 5 in reality in the field?
Pretty high. Doesn't give you a lot of leeway.
It doesn't give you any leeway. You also got to remember, if you read the city spec, once you come up with an optimum AC content, then I believe you're plus or minus 0.25 from your recommended. But you still got to be between 5 and 6. So, what do we do? If this happened in the real world, what would you do? Now, that's why I'm going to resubmit the sheet to you. If you can see, because of our specific gravities of the aggregates, they're pretty low. And GMM, obviously, is a function of the aggregates, just as is everything else. Same with the bulk specific gravity of the mix. These typically should be somewhat higher. You can see here as the VMAs, 14.7, 14.2, 14, and they're still dropping. They dropped a bit and then going up. When we've done GMMs in the lab, remember we had mentioned, and Ray had mentioned that in the mix design video, you got to condition that asphalt after you mix it back in the oven for 2 hours to allow for absorption. When we physically have done these labs in the past, we eliminate that because we don't have the time. We only have a 2-hour lab. So that means you got to mix it and compact it. 3 briquettes plus the other one for GMM. So we always eliminate that. Many times our GMM is lower than our GMB, which can't be. It's impossible. You'd be at negative air voids. So what I'm going to do is you've handed in your lab as far as calculating GMB and GMM stability and flow, and that's fine. That's a typical lab. That's what you do in the real world. Now we're going to forget about that. I'm going to give you other data here, just to make it easier for you guys. I'm going to make it such, because I'm going to do virtuals, such that your VMA will be in spec. And so that means I got to play around with GMB and GMM. Now, because we have problems getting our GMM because we didn't condition it for a minimum 2 hours in the oven, there's another way of calculating it without actually having to physically run the test. If you didn't physically run the test, you know, spreading it out, putting it in the bowl, filling it with the water, weighing it, based on this data, how could you calculate GMM? Anybody? If you didn't physically run, you knew the AC content, you knew the specific gravity of the aggregates, you knew the specific gravity of the AC, how could you calculate a voidless mix, GMM or density, whatever you want to call it? Remember that PowerPoint presentation with the blue when we went a couple of last week when we went over the physical properties? What's density? What's the formula for density?
Mass over volume.
Hey, let's look at this one here. Do we have a mass? That example? What's the mass of our mix? Asphalt plus aggregate, right? That would be the mass of the total mix, right? Would it not? Someone told me yes before, okay? So there's our mass. What's the volume of our mix? Well, remember, if it's a voidless mix, the volume of AC plus the volume of aggregate equals the volume of the mix, right? So I've got mass, right? 1253.2, adding these two together. The volume is the volume of AC plus the volume of aggregate. Well, the volume of AC is 50.3 divided by 1.028. Okay, gives me volume. Density is mass over volume. Volume is equal to mass over density. So now I can calculate the volume of my AC. The volume of my aggregate is mass of aggregate divided by the specific gravity gives me my volume. So now I have my volume of AC. I have my volume of aggregate. I total them. I now have my volume of my mix. It's voidless. I have no air in it. So now I can calculate GMM. And that's what we had to physically do in the labs because we could not get our GMM. We ran the test. We did the whole procedure that Ray showed you. But the numbers, because we didn't allow absorption to take place, we didn't have the time to cure it for 2 hours in the oven. I guess we could have done it the week after, but time just doesn't allow that. So in the real world, when you're doing a mix design in a lab, you would batch it and you would put it in the oven for conditioning, minimum 2 hours. Then your GMM, if everything else is done correctly, you should be okay. But we would physically have values here sometimes below our bulk. Bulk is pretty straightforward. There's very seldom any problems with bulk. You know, briquettes are fairly easy to weigh in air, SSD, and weight in water. But the GMM, because of the conditioning, that's the problem. Do we assume it as 1? Nope, not the volume. Well, you would have to calculate. And if we go, if I could quickly find, if you go back to that lab lecture that we talked about, where we looked at that example where we're calculating all the physical properties, prior to that, it shows you. Let me just quickly find it here, guys. Just give me a minute. And then we can, it'll refresh your memories, I'm pretty sure. Okay. Biometric properties, here we go. This will give it the same thing. This is a little bit different, but it'll be the same. Okay. Start sharing here. Just give me a minute here. Okay. Remember, this was in blue. This is just a different version of it. But, okay, there's bulk specific gravity of a compacted mix. This is a GMB. Remember? It's the mass of the mix divided by the volume of the mix, but also includes the air voids. Okay, so you go through it. Here now, this is what I just did. Mass of aggregate, 50.3, whatever it was 1,202 grams. The volume of the aggregate would be the mass of the aggregate divided by its own specific gravity, plus the mass of the AC divided by specific gravity of the AC. That's a voidless mix. There it is. Mass of dry sample. This would, if you were physically doing it in the lab and you would weight in air and weight in water. Okay? But there it is there. We know the mass of the aggregate. When I was in industry, we would sometimes just run a specific gravity. You don't have to run a specific gravity, sorry, you don't have to run a maximum theoretical specific gravity on every AC content. It's not going to change. You do it, typically you try and do it close to optimum. So say around 5%. You would take a 5% and run this GMM on it. Aggregates are the same. Absorptions are the same. So really, your specific gravity, GMM, should be the same, whether it's 4%, 5%, 6%, whatever. So in industry, we didn't always run. We would just calculate it this way. Why not? It's doable. Okay, so this is where it comes into play. We're understanding the technology behind the mixed designs. And then, granted, it takes time if you've never been involved with it. But so when we found out from the various groups, some of them had negatives because they're GMM. Some GMMs worked out. It depends. Depends if you had higher AC content, it may have absorbed quicker, whatever. But I would then have the students calculate their specific gravity, GMM, manually this way, if you want to call it manual. Okay, just go back now to the Excel. Okay, so they would calculate this manually, and once you had it, then you could calculate the GSE. Okay. Any questions? Because here you can see that the effective specific gravity of the aggregates is dependent on L8, which here is your GMM. So we would physically determine these by the formula we just looked at. So what I'm going to do is, because these values are somewhat low, I will put up another spreadsheet. We'll have these. Okay, that's already given. I'll give you 1.028, so we're all using the same one. And I will give you this, and I will give you this. Stability and flow, I will give you that also, because you're now not dependent on the other group's data. Now responsible, each group now is responsible to calculating all these physical properties for all these AC contents, okay? That way you don't have to rely on anybody. There's 3 of you guys in a group. Somebody calculates the first 3 and somebody calculates the last 3, depending on group 2. There's only, I keep getting an error message, I gotta find it. Group 2, either you want to go up to 6%, because there's only 5 groups. Okay. Any questions so far? When you do this, plot everything up, then you analyze it, then you write a report stating what was done briefly. You don't go into a lot of details, just mention the fact that obviously you did a mixed design, properties and curves were developed, and from the data, you analyzed it, and you would tell me what is the job mix formula. So in other words, you're going to tell me the optimum AC content. And at that optimum AC content, you're going to tell me what the air voids happen to be, the VMA happens to be, what the stability happens to be, and so forth. Okay. Any questions so far? These numbers are going to change now somewhat once I change these GMB and GMM. But anyways, you've got that blank spreadsheet, and that's what you're going to work off. Any questions? That's it for the lab. So now, don't wait till the last minute. If you have any concerns, any issues, let me know. This one doesn't have to be submitted now until the 27th. So you basically got this week and next week to work on it. And then that's done. Who here mentioned a while ago about burn-offs? Was that you, Fabian? Can't remember.
That was me, Sean.
Yeah. Who's me? Sean. We do have an addition oven at B109. And we used to go through an example. I didn't have the students do one because even with a burn-off oven, it took about 40 minutes to run a test. So how, and you're 6 groups, so how could you do 6 burn-offs, as Sean would say? So we would demonstrate one, and then from that you could calculate it. So you'll notice in this lab, I didn't even go into talking about extraction. And what an extraction is actually taking a hot mix sample and putting it in a muffle furnace, once you know its mass, and it burns off the AC. The temperature climbs to like 670 degrees Celsius in these ovens. Phenomenal. So even when you pull that aggregate out, because when you put a hot mix asphalt sample in that oven and it burns off the AC, you pull out, it's clean aggregate. There's no bitumen. Balance the scale, sorry, the oven we have actually has an internal scale. So it'll actually measure the AC. Yeah, you tried it, Ray. Yeah, Ray said he took in 2018-19, it took him 75 minutes. Now, everybody's gone that way because of the environmental issues with trichloroethylene, and supposedly it's carcinogenic. Okay? We used to extract it by putting it into a centrifuge. Put your hot mix in a bowl, almost like your spin washer. You know, your clothes, after they're washed, they're spun dry to a certain degree, and then you go in the dryer. Well, this is what the centrifuge was. We would put the hot mix in a bowl. We would add so many cc's, milliliters of trichloroethylene, which was a solvent. We let it soak for a few minutes, and then we turn it. It would spin, and as it's spinning, the water would drain out. No different than the water draining out of your washing machine, except we're draining trichloroethylene with the effluent. You put another wash in. So after 5 washes, you would pull it out, and you'd have clean aggregate, and that was much quicker. I could run an extraction by the centrifuge in 20, 25 minutes, easy. So I could then quickly tell the contractor out there, hey, your AC's off. Now, 75 minutes, by the time you calculate it, or let's say it's 80 minutes, and an hour and a half, a contractor putting down 500 tons of asphalt an hour, he's now put down 750 tons of asphalt that's out of spec. So here's the importance of getting that AC to the contract from a quality control point of view quickly. There's also Troxler nuclear gauges that'll read AC. It's like a little miniature oven. You put the hot AC in it. It goes through the counts like it does for densities with your nuclear gauge. So you can get them in the field quite quicker. Key issue is to make sure you track that AC as quickly as possible. Because if your plant is wonky or if something's wrong and you put down AC with either too much AC or too little AC, in an hour and a half, you can place a lot of pavement down. Nelson River used to have a plant that could do 500 tons an hour, and he would smoke it. He would lay it down as quickly as a plant can produce it. This guy by the name of Ray Van Lanker, I don't think he's around anymore, but anyhow. Am I using Varsol? Yeah, well, Varsol probably isn't as good. Trichloroethylene is trichloroethylene, is trichloroethane. The ethylene was a little bit more potent. I liked it because it cleans asphalt like you wouldn't believe. Clean our molds, clean our spatulas and everything. I used to have an engineer that would always come in after lunch. And he says, John, I got some food on my tie from lunch. He'd go in the back, he'd take some clean trichloroethylene and he'd dab it. It's a derivative of perchloroethylene, I think, that they used to use in dry cleaning plants. Same thing for dry cleaning. It just, when we dump some on the floor by accident, we would never mop it up. We'd come back in a couple of minutes, it'd be gone. Volatiles just flash off. So, you know, if you're breathing that thing in and day out, maybe if you're washing your hands in it or taking a bath in it, maybe it is carcinogenic. But anyways, maybe we're overcautious in some things. But anyhow, that's an extraction. So you're extracting the AC out of it. And then once we determine the AC content, we now have clean aggregate, right? So we would sieve it. So now we would see how the sieve is coming in the field, actually batching. You know, they batched asphalt, and now we took the AC out of it. We're left with aggregate. You could sieve it. Does it meet your blended sieve? Okay, and you got that plus or minus. So those of you that have maybe worked in the asphalt industry, and like Sean, you obviously have, so how it all comes to play. So It takes a while to understand mix designs, but once you get on top of it, now the rest, you got to calibrate a plant now to make sure the plant will give you what you've designed. That's a totally new, different ball game. Okay, so what I'll do is I will give another spreadsheet that I gave you, and I want you to have a look at it. I could have left everything alone. Okay, I could have left everything alone and then have you guys comment on the fact that VMAs are out. The answer to this is probably do a different mix design. Check your aggregates again. Okay. Check, maybe rerun some of the tests. Maybe some of the tests would have been wrong. I know where this is wrong. It's virtual. Okay, so I get results from past years, and I got to manipulate them a little bit because our values this year for our blend was different than we used in the other past. Okay. Ray, you said MI uses Varsol. So they do use a spin centrifuge. What were the results like? I mean, was it a good cleaning or did it take forever?
Yeah, Emma uses Varsol. It takes forever.
Well, if you're going to use Varsol, why wouldn't they just use Try?
Maybe because of the chemical or, the negative issue that comes up with Ryclo. But yeah, they uses Varsol since maybe I was there 2018. Yeah, I think longer than 5 years, I would say. But
Well, I mean, Varsol is acceptable, but it
Mhm.
takes forever to clean.
it
Whereas if
takes
you
forever.
ran,
Mhm.
you can still buy trichloroethylene, Harrison Crossfields, hair cross, I call it that. You can still get it because I know the industry still uses it, like Hermie uses it, right?
Yeah.
And it's great. I've always asked Hermie for some because it's great. After we do these physical labs, our molds are dirty and everything else. And I think Art uses Varsol probably for cleaning. But if you use trichloroethylene, put it in a 5-gallon pail, drop all your molds in it. 10 minutes later, you pull them out, they're clean as a whistle. Because all the sand and
Yeah.
fines that
Mhm.
are adhering to the mold after you've done your cleaning, it's in the bottom of the pour off.
Mhm.
Okay, and then I would use dirty trichloroethylene for cleaning. I wouldn't use it for new testing, but I would use it for cleaning tools because there's still a lot of potency in it. Okay.
Yeah, I just need like maybe one pail and then, or not even, maybe like a bucket and just put everything in there
Oh yeah,
for 5 minutes, 10 minutes, and that's it.
Yeah.
Yeah.
all your spatulas, all your mixing spoons, and
Yeah,
even
molds.
wet a rag and try and clean the bottom of your Marshall hammer.
Yeah.
Cleaning the base plate. Oh, it's cats. Now, I wish I could get some here around the house. But also, one guy told me that brake fluid. You read the ingredients on brake fluid. Brake fluid is something like 90% Try.
Okay.
So brake fluid you can buy at Canadian Tire.
I'm not sure if I've seen Varsol in car seat.
Oh, there is Varsol in car seat.
I think I used that when I was cleaning my tools.
Well, I use Varsol when we do the specific gravity labs on AC. Remember, cleaning the little
Oh yeah.
thermometers. Yeah, we do use Varsol, but if you could get trichloroethylene. But again, the health concerns, people are concerned that, once it's labeled carcinogenic,
Mm-hmm.
you have to be careful. Plus, one of them is an ozone depleter. From my understanding, I think it's trichloroethylene. Supposedly depletes the ozone.
But they're still producing Ryclo.
Oh, yeah.
Yeah.
I mean, you get an MSD sheets, and if you take the
Mhm.
precautions, if you use a respirator, you use rubber gloves, to me.
Yeah, every year we get like at least 10 buckets every year.
Yep.
Yeah.
I did a little project with Mulder Construction, and the guy had a brand new Mulder jacket, like a company jacket. He was brand new.
Mhm.
And he went down to the asphalt plant, and they were loading up bitumen from Jade, was pumping it up,
Mhm.
and the
Yeah.
hose blew. And he got sprayed with AC all over his coat. Brand new jacket, company jacket. So I
Right.
came up with a lab that I had on site. I had a portable lab. and he asked me if I had any try, and I had a brand new pail of it. So I said to him, well, give it here. So I opened up the pail, I took the jacket and I just stuck it in, closed the lid, and I said, let's go for lunch. So we went for lunch. Half hour later, we came back,
Mhm.
pulled the jacket out,
Yeah.
let it drip, and then we hung it on the handle of a shovel.
Yeah, it dries faster.
Then 15 minutes it was dry, and it
Mhm.
was clean, like brand new. Dry clean.
Yeah, I use dry cloak for everything, like cleaning the table.
Yep.
Yeah, I know it's carcinogenic, but you just have to wear proper PPE.
Yeah, exactly.
The one with the filter on the left and right side. That's
I
what we
mean,
use.
this engineer used to come in and he'd clean his tie. I mean, he would just take a little spot on a paper towel and dab the tie, and it would clean it, like leave.
Yeah, and 95 mass is not enough.
Exactly.
Yeah, and then you have to.
Yeah, I think you got to bath in it every day before you get. Neither here nor there. Okay, we're getting off the topic. So we didn't cover extractions here, but there's another test that is done in the field where you're determining the AC content. So when you sample an asphalt mix from the plant, from the roadway, wherever, the tests that you would run on it are AC, like an extraction, or AC content, burn off if you want to call it. You'd run the gradation, you'd compact your briquettes, you would do the bulk specific gravity on the briquettes. You would also split that sample down before briquettes. You would put one in for maximum theoretical specific gravity. Then you do stabilities and flow on those briquettes after you've done your bulk specific gravities. And then you write up the report. And that was the control, quality control. So every time you take a sample, now they're asking for a complete analysis. At one time, we used to just do a complete analysis, I think on 1,000 tones or 2,000 tones, but we would do an AC and gradation on every 500 tons of asphalt placed. The AC content was good and the gradation was good. There's really no reason why your VMAs and avoids and bulk specific gravities and everything else wouldn't be good. So it was a quick test. Okay, and then we would do a complete after so many tones. Anyhow, any questions on this, guys? So every group now is going to calculate all the properties for every AC content, like group one. And if you're in group two, you're using group two data. So here you can see this is group one, and I would have one here for group two. Man, okay. But I will give you, like say, these values are going to be somewhat different now. Stability and flow shouldn't be any different. But because you only calculated your own, I will put them in. There's no point going to lab 8 and dig out each one. I will give you those, okay? Any questions so far? Remember when you're calculating percent bitumen is this column, because it's the actual. It may not be exactly 4, 4.5, 5, 5.5, whatever. And I'll look at these again. These may change a little bit, but the next spreadsheet will be the one that you're working on for lab 9. Any questions? Here's mud. You were in Natalie's class, clear as mud? Oh, okay. Well, if there's any questions, let me know. Don't wait last minute. Now you guys know how to design asphalts. Mix asphalt. Okay. Okay, we're free to go, guys. Have a good week. Yeah, go ahead.
Are you available to meet for a couple questions?
Sure can. Who am I speaking to? Oh, Kelly. Yeah.
Kelly, yeah.
You want to meet right now? Like, hold on until